So in the stripping column, again we will choose a rad frag column. This time let us choose this type of icon. And let us increase the size a bit. Okay. Let us rename it as stripper, STR. Now for stripper, we have some information. Go to the relevant chapter. Yes, model validation of stripper. Here it says, in the stripping section case study, we have two different pilot plant facilities considered. One is CO2 capture facility from Syntef material chemistry described in Tobiasen et al. And it is available in this reference. And the other one is a pilot plant from University of Texas at Austin, described by Dugas, found at this reference. What is the difference? Difference between the two cases found in the configuration of the water stream exiting from the condenser. In the first case, in Syntef, water is mixed with the liquid exiting from the bottom of the stripper and then sent to the reboiler. So that means if we have a condenser over here in the column, this is the condenser and this is the reboiler. So this liquid stream is added with the reboiler. It is sent to the reboiler. Okay. And in UTA case, the same stream is sent back to the top of the column as reflux. So in UTA case, it is given like this. And for the first case, it is sent like this. Now we will choose this one, Tobiasen et al. Okay. Now again, why we are choosing it? Just for the sake of it. When you do the practice problem, you can choose Dugas reference also. Go back to simulation. Now, as we have to do such type of changes in the condenser and reboiler output, we cannot use the condenser and reboiler integrated with the column, because the condenser and reboiler which are integrated with the column has its own configuration which we cannot change. So we shall use two flashes, one at the top, another at the bottom. The top flash will be regarded as the condenser and the bottom flash will be regarded as the reboiler. And we will do the configuration at our choice. So for that, we choose one flash at the top, which will be our condenser, and at the bottom, which will be our reboiler. So we name it accordingly. This is our condenser, and this is our reboiler. Okay. So as it is said, water stream exiting the condenser, it is mixed with the liquid exiting the bottom of the stripper and then sent to the reboiler. So basically, this stream is sent to the reboiler, and this stream also is sent to the reboiler. Mixing means you can use a mixer, but even otherwise you can just throw in inside the reboiler. Either way it will work. Okay, and then this is the stream in, this is the stripper outlet to the condenser, and this stream should be pure CO2. If not pure, it is mostly CO2. All other things have been knocked off. So we shall rename them accordingly. We'll rename it as STR in. This is STR vapor. This is STR liquid. This is condenser liquid, and this is CO2. And one more output is left, this one. Actually two outputs. One is reboiler output, which is going inside the stripper back. Okay. So this one is reboiler recycle, and this one is reboiler vapor that is going inside the column again. First we have to check what is the feed in the streamline. For that, let us choose the Tobiasen case. Its temperature is 389.91 Kelvin. So 389.91 Kelvin. Pressure 196.96. So 196.96 of kilopascal. Molar flow rate, it is 10.71 kilomole. Mole fraction, .0348 CO2, MEA 0.1102, and water 0.8549. So total it is coming 0.9999. So let us add one somewhere. Let us add here. That makes 1. Okay, so everything has been given. Now stream in has been given. Stripper, again it is rate based. Number of stages, let us say 20 stages. Again, there is no condenser, no reboiler, because both of them we are using externally. The stream, now stream in will send from the top of the column, and reboiler vapor, it will be added from the bottom at the 20th stage. So on 20th stage. Okay. And then go to the pressure. Now stage 1 pressure has not been set, but as the liquid stream STR in is inserted at the top of the column and its pressure is 196.96 kilopascal. So let us keep the stage 1 pressure also at 196.96 kilopascal. And there is a pressure drop somewhere. Yeah, this is a pressure drop, 1 kilopascal. So condenser pressure drop 1 kilopascal. What about the flash? Flash, it says that it operates at 196.96 kilopascal. The pressure is 196.96 kilopascal. And the temperature, condenser temperature has been given. Okay, 288.15 Kelvin. And already we have entered 196.96 kilopascal at the stage 1. Let us say pressure drop is 0 rather than fixing the pressure once again. We'll say pressure drop is 0. So there is no pressure drop in the condenser. The reboiler, we have the information of reboiler duty, which is 11.6. So it is 11.6 kilowatt of heat duty with 0 pressure drop. There is no pressure drop in the reboiler as well. So reboiler is done. So condenser, reboiler, yeah. As it is a rate-based column, so we have to fix the column internals, add new, there, add a new section, and extend the section from 1 to 20 so that it is a single section column. Its mode of calculation, again, it's rating, and type is packed. Packing type, I think it is different. Yeah, it is Melapack 250Y Sulzer. So it is Melapack Sulzer, dimension 250Y. Okay. Height and diameter 3.89 and 0.1. 3.89 and 0.1. Okay. Now go to the rate-based modeling setup. The old stuff, we just repeat them. It is 0.9 reaction condition factor, film discretization ratio of 10, and in this section we'll have a rate-based calculation. And then it will be discretized, the liquid film, with 5 discretization points. We'll consider the vapor phase film. Okay, it is done. And in the rate-based report, we can include the mass transfer rate as well. So the reactions it occurs from stage 1 to stage 20, and the reaction ID is MEA reaction. Okay, so it is done. Okay, so there is a problem with condenser and stripper. Let's check what. Okay, so here I have given condenser pressure drop of 1 kilopascal. Instead of condenser pressure drop, we have to say stage 2 pressure drop, because there is no condenser in the system. And again, so there is an error. Perhaps the reboiler duty is not enough. So we shall increase the reboiler duty to 21.6 and try it once again. So again there is an error in the stripper. So we have to look somewhat carefully what could be the error. Twentieth stage, pressure is 190. Oh, there lies the problem. We are operating at 196.96 bar. So I always say that you have to be very careful about your units. Okay, with the wrong unit, all your simulation will go down the drain. So again, you have to do the simulation, and hopefully it will converge now. Okay, so it has converged without further problem. So let us save this simulation. Now here again we have to check a few profiles. The stripper liquid temperature profile variation. It should look like this. So we go to the stripper block this time. So this is the stripper block. Profile, this is the liquid temperature, convert into Kelvin, and then copy and go to the, yes, this one. So we'll check only this up to this point. Yes, so 390 to 394. I think we have shifted it to chart 1. We'll delete this one. Yes. So from 395 to 390.5. So it has come from 395 to 390.5. Okay. So with 20, it's neither 10 nor 60 nor 70. So we have taken n is equal to 20. So it should be somewhere in between. And I believe that the trend is correct. And if you want to see the CO2 vapor composition, that also is possible. You have to go to the composition, vapor, and mole, CO2, copy, go to sheet 2, press over here. Yes, so this is the chart. So, okay, in this case, the height is not 6.55, the height is 3.89 meter. So we have to change the data. So from 6.55 to 3.89, and here also 3.89. Okay, now it has from 1 to 3.89. The trend is definitely same. Okay, so we can argue that our trend as well as the numbers, they are matching. We have verified the absorption column and the stripper column separately with separate input information. Now we shall add them up. First, we should see what is the temperature and pressure at various ends. So the temperature and pressure at various ends are given over here. Before that, let us refer to the chapter 5, where the design analysis has been integrated. So this is the industrial CO2 post-combustion capture by reactive absorption stripping plant flow sheet. Now here we have to use a heat exchanger and a pump while sending the rich solvent from here to the stripper. So obviously we need a pump because here the pressure is 1 bar and here the pressure is 2 bar. So we need a pump to increase the pressure. And we need a heat exchanger because here it is at 28 degrees centigrade and here it is 117 degrees centigrade. The reboiler output, it is 119 degrees centigrade. So it is expected to transfer the heat from this end to this string through this kind of heat exchanger arrangement. So let us first use a pump. So the pump is over here. And for the time being, let us use a simple heater. Later we can change the heater to heat exchanger. No problem. So the pump will pump it out with a discharge pressure of 196.96 kilopascal, which is actually the pressure at entry point at the top stage of stripper column. So we write it as pump, PMP, and we connect this to the outlet of the absorber. And then the outlet of this pump will go to this heater and another material out from this end to this end. Okay, and we will have one mixer over here. So let us use a mixer. Let us connect this one to this mixer And let us connect the water outlet of the condenser to the mixer instead of the reboiler. Here the configuration has changed. So we have to reconnect this stream with a new destination, which is over here. Okay. So we will keep it over here, and this one will keep it over here. Okay. And outlet of this stream out of the mixer is over here. Okay. And obviously we have to fix the heater. Let us say the heater will go up to 110 degrees centigrade with zero pressure drop. Sorry, it is 117 degrees centigrade with zero pressure drop. Okay. So let us run it. It should not take much time because already it had converged a few minutes back. Let us check. Yeah, so it has converged again. Now the system is ready to connect these two streams. So what we'll do, we will knock off this STR in and add this S13 to STR. So for that, let us cut this and reconnect this one to STR. And now we can safely rename it as STR in. Now obviously the composition of the new STR in will be different. Earlier the composition was 3.48% of CO2, 11.02% of MEA, and 85.49% of water. But right now the condition will be of the rich amine, which is actually almost no carbon dioxide. Instead of 3.58, we are entering with no carbon dioxide, and 95.51% of water we are entering, and MEI is merely 3.75% instead of 11%. So there will be a lot of changes and lot of ions will come in. Okay. Earlier there was no ions in it. Now there will be a lot of ions. Now we have to fix in the connection point of STR in, because earlier we deleted the previous stream. So we have to restate that STR in is at or above stage 1. And now we have to rerun the system. Okay, so again it has converged. We are happy. It didn't take much time. So we save the result. Now you see the temperature has increased to 121 degrees centigrade. Okay. Now let us take a strategy. Now time has come to replace this heater with this heat exchanger, but we'll not completely discard this heater. I'll tell you why. We feel that it is not possible for this stream to pass on enough heat to make it 117 without experiencing the temperature crossover. First, we'll place the heat exchanger over here, and then we shall reconnect this line to this destination and reconnect this line with this source, and we shall rotate this icon, take this stream, reconnect with this destination, take this material stream out, connect with this, take this out, and connect with this. Okay. Now, okay. Now we shall increase it up to 150 degrees centigrade. I'll tell you why I am doing it. Fix the heat exchanger. Let us say shortcut heat exchanger. We will fix the cold stream outlet temperature at 117 degrees centigrade. Okay, rename it as HX. Rename it as H out. Now run it once again. So all other things were already converged, so there should not take much time. Yeah, so it has converged again. Now we will look at the condition. Here, if you say vapor fraction, so this is vapor fraction completely 1. Okay, and here the heat exchanger output, we have vapor fraction 0.85. That means gradually the vapor has started condensing and lot of latent heat is being spent in heating this stream at 28 degrees centigrade to 117 degrees centigrade. Now here you can check the vapor fraction is 1 over here, and here the vapor fraction is 0. That means here it is entirely liquid. Here it is entirely liquid. Here it is entirely liquid. If you check the heat duty, you will find 22 kilowatt. That means 22 kilowatt of duty is required to take this temperature from 28 degrees centigrade to 117 degrees centigrade. Now the temperatures are so close that it is my apprehension that it is not possible for the heat exchanger to take up enough heat from here to bring the temperature from 28 degrees centigrade to 117 degrees centigrade. So what we can do, we can decrease the temperature a bit. So instead of 117, let us take 110 degrees centigrade. so that the temperature difference from this end and this end are a bit higher, and run the simulation once again. Okay, so in the bargain we have got even lesser amount of heat duty that is being carried over here. By decreasing the temperature, we have got a fair estimate that perhaps now we have enough amount of heat duty that we can transfer from this stream to this stream. Now let us decrease it from 150 to say 130 and check what happens. Okay, so you can see that it has come to 70% of vapor fraction. So we can still decrease the temperature, say to 125 degrees centigrade, and run it once again. Okay, so now it has almost come to the level. Let us make it to 121. It is very close though. Okay, so it has almost no latent heat at all. Okay, so let us save it and then change it. Make it 120 now and see whether it can converge. Yeah, so it has safely converged. Now you can see that it is showing heat duty 0. That means this heater is not at all working. Its temperature is same, 120. And a stream of temperature 120 degrees centigrade is able to offer enough heat duty for this heat exchanger to work. So now what we can do, we can simply delete this one, and we can delete this stream as well, and we can reconnect with this destination. Okay, and we run it once again. Yes, so it has converged. Okay, so we can save it. So now you can see how small this temperature is. It's only 33 degrees centigrade. Okay, so almost we are able to exchange entire amount of heat. Now the purpose of vapor fraction is over. Now we can just untick it to reduce the clutter. Now the recycle stream is having the temperature of 32 degrees centigrade and it is at 2 atmosphere pressure. Now it has to come to 1 atmosphere pressure, or to be very specific, it should be 103.15 kilopascal pressure, and the temperature has to be 19 degrees centigrade in order to make it usable over here. Now for that, refer to this. Here they have asked us to use a pump and a cooler. But pump is not necessary because it is already at 2 atmosphere pressure. There is no need to pump it to a higher pressure. Rather, we have to use a valve over here so that we can reduce the pressure to 103.15 kilopascal. And obviously we need a cooler to cool down the temperature from 32 degrees centigrade to 90 degrees centigrade. So we need a valve over here and one cooler in series. Okay, so rotate this icon and this icon also. This one is cooler, and this one is valve. So that's how we rename it. And we connect this and this material connection from this to this, and this is the outlet. Okay. Now rename it as mixer. Rename it as M out. Rename it as V out. Rename it as recycle. Okay. And then we have to specify the outlet pressure of the valve or discharge pressure of the valve, and that is 103.15 kilopascal, because that is the pressure at which lean amine enters the column. And the cooler output, it should be 19 degrees centigrade, or we can refer to this one once again. So it is 292.15 Kelvin. So it is 292.15 Kelvin and 0 bar pressure drop. Okay, now you can run it once again. Okay, so it has run and it has converged also. So save it, and we have come to the last portion of our task, that we have to recycle it. Okay. Before that, let us see the results of recycle and compare with the original lean stream. Okay. Now the temperature and pressure are same. The molar enthalpy, mass enthalpy, molar entropy, mass entropy, the densities, everything are comparable. The molar flow rates are also comparable. But the mole fraction is somewhat different. MEA, the lean phase, it was 5.48%, whereas in the recycle stream it is 3.97%. Water, it was 94.48% in the lean stream. It is almost comparable in recycle stream. There was no CO2 in either stream. There is CO2 obviously in recycle stream, but they are in the form of CO3 minus minus, MEA, CO minus, etc. Now the question is whether we can directly remove the lean stream and add the recycle stream in its place. In other words, whether we can do like this. If it is possible, then our job will be much simpler. We'll just open the absorber and we will tell that we are feeding the recycle stream at stage number 1. Okay? And then we can run it. Let us see whether this thing works. So let us open the control panel. There will be a lot of changes in between. We'll just keep on observing. Okay, absorber converges. Stripper also getting converged. Yeah, it's a good sign. But iteration 1, it says 18 variables are not converged. Okay. So we are at iteration number 2. The stripper and absorber, they are not creating any problem, but again 19 variables are not converged. Here, iteration number 3, 18 variables are not converged. Iteration number 4, 16 variables not converged. Then 16 variables become 17 variables. Instead of going down, it is going up. Okay, iteration number 16, it says 15 variables not converged. And so on. Let us see how long it goes. So we have waited up to 35 iterations, and there is no sign that it will come to a convergence very soon. Still, we are hovering around 17 variables which are not converged. So what we will do, we will stop over here and take some other strategy. Now it's a known fact that converging a recycle stream is a tricky thing. It is not always possible to converge a stream very easily. There are various techniques. One of them is tearing a stream. So in this method, you have to tear a stream in two parts. One is inlet, the other one is outlet. So you have to set in the inlet to such a condition that the outlet at the other end also is same. For instance, suppose you delete this stream and recycle it back, and then you can tear this particular stream. That means this is an inlet stream and this is an outlet stream. This is in, this is out, there is no connection between them. And you can manipulate the inlet stream and its condition in such a way that the condition of the outlet stream is same. I mean, after the simulation, it comes to be the same. So once this inlet stream and outlet stream conditions are exactly same or somewhat similar, very close, then you can just delete one of them and connect the other end. In such situation, it will be very easy to converge a solution. Now, there are many other ways of converging recycle stream. If you study various literature and study material or video on Aspen Tech, you will find various other techniques. But one technique that I am going to teach you, you won't find it in any other study material or other video, because that technique I have found myself while working with Aspen Tech, which I am going to teach you now. For that, you need 2 splitter and 1 mixer. So suppose you have a splitter over here and 1 splitter over here, and you will get 1 mixer. Okay, say this is splitter 1, this is splitter 2, and rotate this icon, just flip vertically. This is mixer. Okay. Now we shall reconnect the stream to this destination. Reconnect this stream to this destination. Then connect this to this destination and connect this to this destination, and the mixer output we connect to this one, and then one output will be in this one, and here the output will be like this. Now rename it as R lean and rename it as R recycle. This is M in. The M in will go into the first stage. Okay. Now we have two blocks to fix. First one is the SP1, that is the block over here, and second block is SP2. Okay. SP1, we will say that R lean is 0.99, SP2, R recycle is 0.01. Now look at this, what we have done. We have used a splitter where the lean amine has been splitted into two parts. 99% is going over here, 1% is being rejected, and the recycle stream, only 1% is added over here, 99% is rejected. These two are mixed, and the mixed flow is being sent into this particular absorber. Okay, so run this. Now, although we have done some changes, but the lean amine, it is still 99%, and recycle only 1%. So only 1% change I have introduced into the system, and the recycle loop is connected. In most of the cases, this thing will converge because the amount of recycle is very, very small. It is just 1%. Okay? Yes, it has converged. So we save it first. Okay? So we have saved it. Now in this case, you can add in the molar flow rate, and let us not bother about the temperature and pressure at this moment because these informations are not of that much of relevance, and heat information is also not needed. Instead, we are watching the mass flow rate and molar flow rate. So here we find the mass flow rate is 223 and molar flow rate is 11. Okay. Now we decrease the lean amine portion to 95% and increase the recycle portion to 5%. Okay. Then run. So gradually we will decrease the fresh amine and increase the recycle. So it has converged again. Okay. Now you decrease it further, make it 90%, and this one you make it 10%. Okay, run it. Again it has converged. Now every time you can see the mass flow rate is gradually increasing. Earlier it was 223, now it is 224 kg per hour. And next time you can change it to 80% and this thing to 20%, run it. Again it has converged. Now we have become a little bit adventurous. So we reduce down from 80% to 60%, a big jump. And there we increase it to 20% to 40% and run it. Well, it has converged again. So it gives us more confidence in decreasing the lean amine further to say 6 to 40%, another 20% jump, and lift the other one from 40% to 60%. Run once again. So it has converged again. Now you can see 138 kg per hour of recycle stream is being entered over here. Only 89 kg per hour of fresh amines. Okay. So we reduce it down further less, 0.2, and increase it to 0.8. So it has converged again, and you can see 185 kg per hour recycle stream we are entering, while 45 kg per hour is the fresh amine. So we will do one more, just reduce it to 10% and increase it to 90%. This is the last thing that we are going to do. So it has converged once again. Now you can see out of 235 kg per hour of recycle stream, we are using 212 kg per hour. Only 22 kg per hour of fresh amine we are using, and 24 kg per hour of the recycle we are just throwing it back. Okay, here you will notice although we have got some result, but we are having some warning of convergence. Streams crossing the loop converged by solver are not in mass balance. Okay, there is a problem of the mass balance, mainly because earlier when we were sending lean amine, it was only 223 kg per hour, but we have increased it to 234. So 11 kg per hour we have increased. As the mass flow rate has increased, perhaps 0.1 meter diameter column is not enough. There may be the problem of flooding over here. What we may argue that, well, this splitter we do not need. Instead, we will give 10% of the lean amine over here. So this one also we can delete. Cut. And we can cut this as well. And we can reconnect, and we can change its value. So instead of 3.04, we can give 10%, so it is 0.304. In that case, we do not have to use any splitter. Directly we can enter this lean amine to the mixer, which will get mixed with the 90% of this recycle. 10% anyway, it is going out as a waste. So this gives us an idea that although recycle stream is having all the amines, but we cannot use them entirely. We have to throw some amine out and replenish with some fresh amine. And that is exactly what is done in real life scenario. In the industrial usage, you really cannot use the total amount of amine in the recycle mode. You have to add in some fresh amine always. Okay. And finally, if you want to store your simulation results in proper format, you can do it by exporting the result into Microsoft Excel file. For that, you have to go to the result summary, go to streams, and here you will find the send to Excel ASW. So just click it. It will give the option, and you can add the table to existing workbook, or you can take it to a new one. So it says export tables to Excel, and suppose you want to send it to CO2 MEA .xls. Okay, save. Then you will find the progress over here. This is the material stream that is going to the stream, and export to Excel file completed successfully. Now you can open the Excel file. So the CO2MEA.xls has been opened. So you can check all the result in a single sheet. Okay. And if you want to generate a report, then you can do it by pressing this report over here. Suppose you want to get a report of the absorption column. So just click on the report and say generate report. And it will generate a report like this. So it is hydraulic analysis report of the absorption column. So these are the contents. This is the column internal summary, number of stages, total height 6.55 meter, the head loss, pressure drop. Okay. So it is packed bed with burl saddles. Then it will give you the feed summary, packing geometry, and here column diameter and other things are given. And very importantly, the column internals, that is the operating point at each and every stage. So it is stage 1, then it will be stage 2, stage 3, stage 4, stage 5, up to stage 30 it has generated. Okay, all the reports will be generated like this. So with this we come to the end of this lecture of this week. In the next week we'll come back with yet another interesting case study. Till then, thank you and goodbye.